Just checking briefly with the remote audience, anyone who's zoomed in of the tACS Challenge Steering Committee, can you hear me?
Yes, we can hear you.
Yes. Excellent, we can hear you too, so that works. Fantastic. That's not always a given for hybrid meetings. So I'm just going to minimize the view of the Zoom participants so that we can see the entire screen here. Which just means that raising your hand won't work because I won't see you. So you would need to unmute and just interrupt me if you would like to add something, which is completely fine with me. So I'm happy to represent the tACS Challenge Steering Committee. All the work and ideas I'm going to present are not just mine, it's of all these people shown here, and actually many more. So we have started this initiative actually in 2018 during a meeting in Cambridge, organized also by Benedikt Zofel, and then quickly after we met here in Rovereto in 2018 for the first time, and decided on a paradigm together, and since then we had more or less regular in-person meetings, but also a lot of online meetings with the steering committee. And while the pandemic slowed everything down quite a bit, and also because this is like a side project of all of us, and we don't have explicit funding basically for this project, it just took a while. But I'm actually very proud to say it didn't die, right? So within 4 years, the project did not die, but it actually developed. And we're now at a much more developed state than 4 years ago. So let's jump into this. What I'm going to talk about today is basically an update on the protocol after all the piloting and development work that we did over the years. Going to give a very short introduction, talking about this, and then focus on the methods, the behavioral paradigm, the simulation protocol, certain materials that have been developed, and the procedures, and then talk about next steps. I would like to thank in particular, of course, the Rovereto team here for organizing this and hosting this event again and again. Then the team from Neil Grossman's lab for building one of the important devices, the Arduino device I'm going to show you later. Umer Hassan from my lab who also developed a lot of parts like the tACS cap and montage switching solutions, and the extensive testing of the setup. Florian Kasten also tested the behavioral setup quite a bit. Mircea van der Plas from Simon Hanselmeyer's group did a lot of organization in the beginning and also testing of the protocol. Elena Tonoli was testing the protocol here. Axel did all the simulations. Benedikt built the analysis pipeline, and many more, right? So it's not all of us, we've been all discussing and having good ideas, but a lot of people also did the groundwork. So this is not even an up-to-date list. I think it's an old one, but just to show, there are many labs, and we have to now recheck who is actually going to participate 4 years later. And also, just a very quick recap, not going into any particular details. We decided to not particularly investigate the role of alpha oscillations or anything, but we were inspired by the work that had been done on alpha oscillations in the individual system, and the idea that they would modulate in a phasic manner cortical excitability. And of course, the related work, and also this is an old slide from, I think, 4 years ago, so stuff has happened since then, I just didn't update. There's evidence that tACS at 10 Hertz has a phasic effect on certain behavioral outcomes. So this is why we eventually ended up also with the 10 Hertz protocol here. But the general hypothesis is way more simple and more general. So the idea is, I want to test whether tACS can produce rhythmic online effects on behavior at the stimulation frequency that likely result from phasic current modulation in the brain and not from sensory confounds. We've heard about the cutaneous confounds and also phosphine confounds. So it's not about showing that there's neuronal entrainment. That is way more difficult, requires EEG, MEG, artifact correction that to date is still not working properly. But we want to show the behavioral effect. And more specifically, we want to test whether 10 Hz tACS at roughly 2 milliamp of the visual cortex, but not retinal or cutaneous control stimulation protocols, causes phase-dependent fluctuations in the detection performance of near-threshold luminance variations in visual stimuli. So this is now the specified version of it. So, this is, so we're not assuming frequency specificity. We're not saying it works with 10 Hz because of alpha oscillations, doesn't work with 20 Hz, or doesn't work with 5. That's not going to be tested, right? It might work. And we're not assuming a particular neurobiological mechanism. That's not part of this endeavor. But the idea is to have a clear hypothesis and a large number, very good control conditions and a large sample to make sure once and for all whether tACS has these kind of very straightforward excitability-driven effects. So let's go into the methods, because this is mainly an update of what we have developed since then. The behavioral paradigm is going to be one where we have an LED array with a fixation LED and then 5 target LEDs in the lower visual field. Every now and then, without any particular cue, one of the LEDs will change its luminance, just slightly, and we're going to titrate that. And at the same time, we're stimulating the visual cortex with 10 Hz tACS. And whenever one of these LEDs is varied in luminance, so a target happens, we're going to measure the phase of tACS at that time, and then evaluate detection performance as a function of tACS phase. Very straightforward. To do so, we decided to not rely on complicated setups that would differ from lab to lab, but actually build an Arduino-based control unit. What you see here is ACB, CBA, BAC, etc. are 3 different montages that I'm going to talk about in a few minutes about in a bit more detail. And it's organized in a kind of Latin square with pseudo-randomization, so it's balancing the order and position effects, even though we only have like 3 repetitions per subject of each montage. So, just to recap, the target stimuli are these 3 millimeter LEDs that are placed in a certain half circle, 0.7 visual degree angle radius. Participant is seated like 1 meter away. LEDs are continuously lit, but then briefly changed in luminance. And we will have about 450 stimuli per montage condition. ISI of about 1.5 to 7 seconds with a mean of 2.8 and a standard deviation of 0.7 with a log linear distribution of the events to prevent predictability. So it's, even though it's relatively fast, right, to produce a large number of events that we can use for the averaging procedure later, it's still unpredictable for the participant when the next target would happen. This results in a duration of 21 minutes per condition, also means like 21 minutes of actual cortical stimulation, which is in typical range, and we split it in 3 blocks of 7 minutes. Hits, because these events uncued, basically means the button, the response button, has been pressed during a certain time period that we have defined as 150 to 1,200 milliseconds after the event, So if the button press happens during the time period, we think, okay, it's actually due to they've seen something or thought they have seen something. If it's not pressed during the time period, it's a miss. If it's pressed outside the time period, it's a false alarm. We do not have correct rejections because it's like an unqueued paradigm. Oh, okay, I messed up the animation here, but so focus on the occipital montage, our main experimental montage. These E-field simulations have been done by Axel Thielscher. This is an optimized montage to produce strong E-fields in the visual cortex. It's in primary visual cortex. We use 3 2.5 centimeter diameter electrodes in the back, electrode positions OZ, O1, and O2, versus larger 4.5 centimeter diameter electrodes at ZPZ, ZP5, and ZP6. Why is that? So we want to maximize the current in a large visual cortical area, but we don't want any kind of phosphenes. We don't want the current to return via the eyeballs. So we have these large electrodes here as some kind of crown to catch all the currents before they would actually go right to the frontal cortex or enter through the eyeballs. And this works pretty nicely. Also here, the normal field has been shown by Axel to show that since this is tACS, large portions of the visual cortex actually receive the same phase at the same time, right? With the sterification problem, and depending on the direction of the current, would otherwise hit relevant cortical areas like anodal, cathodal stimulation, and here it's relatively homogeneous. Then with this retinal control stimulation, there two electrodes are added. You will see that on another picture later a bit better. Below the eyes, small electrodes here. Also, I just switched the titles here. I'm sorry. So this is the cutaneous control condition, right? So sorry for that mix-up. Basically, these are new images that Axel sent me last night, and I just put them in. So this is my bad. So the cutaneous control stimulation is one where we use a shunting montage where actually we don't use the large electrodes at all, but only have O1 and O2 against OZ. So the current is going just through the skin, causing stimulation of peripheral nerves in the skin so that you can feel it, but it hardly enters the brain, right? So this is calculated for a 2 milliamp peak-to-peak amplitude, and there's very little stimulation of the visual cortex. And then we have the retinal control, where we have these two electrodes added below the eyes, and again use those here as like for the second channel. So for the like as a return electrode, so it's all just done with one channel, right? So I also like two sets of electrodes which are connected against each other. So basically, current is flowing in between these two electrodes below the eyeballs and these three electrodes at CP. And what happens here is we get very strong currents in the retina, because tACS can produce retinal phosphenes, as we know, and but this montage will not produce any direct transcranial stimulation of the occipital cortex. And each of these montages will, of course, be titrated with respect to its intensity separately, so that we produce the effects that we are after. So when choosing the stimulation intensity for the occipital montage, the idea is to have 2 milliamp peak-to-peak amplitude or 90% of the individual maximum intensity without phosphines and without rhythmic cutaneous sensations. So that means we target for 2 milliamp, but if they start seeing phosphines before that, we would use a lower intensity, namely 90% of phosphine threshold. If they start feeling rhythmic cutaneous sensations beforehand, we would go to 90% of that. So we want to make sure that we have no rhythmic phosphines and no rhythmic cutaneous sensations, because that would definitely disturb the paradigm. So we have to stay below that. Non-rhythmic cutaneous sensations are acceptable, because it's really hard to stimulate at proper intensities without feeling anything, right? You get some tingling sensation, some heating maybe, but if it's continuous, it's fine. It just shouldn't entrain the cortex. The phosphine control montage, or retinal control montage, uses 90% of phosphine threshold as produced by this montage. Again, we have to stay below phosphine threshold, otherwise the protocol won't work anymore, but we go to 90% of that. And for the cutaneous control montage, 90% of rhythmic cutaneous sensation threshold. Some labs will be able to use topical anesthesia, like Emla cream, lidocaine cream, to reduce these cutaneous sensations, and are thereby able to reach higher intensities. We say some labs because some groups have indicated that they would have difficulties getting ethical approval for that, others won't. So we will have like subgroups. Some will be able to use higher intensities than others. We'll have questionnaires to be filled after each block with respect to phosphines and cutaneous sensations to be able to document at least what has been actually perceived. Now, how to do this? I'm going to talk about the Arduino device, the tACS cap, montage switching device, and provide an equipment list and costs. So near Grossman's lab built this Arduino control box. We do have a basically also a button box. We do have a so one important thing is to know which phase of tACS is actually happening at the time when randomly these target stimuli are applied. We have to record the tACS signal, and because not all the participating groups will have like an output signal from the tACS machine, we decided to just measure from the scalp the current, and that can be fed into the system. The Arduino system is controlling this LED array that you can just mount somewhere on the screen, for example, on a tripod. And there is a software graphical user interface to do the titration in the beginning, and so it's MATLAB based. And we're also thinking about maybe providing a standalone option for that. And so there will be a perceptual threshold titration. I'll go a bit more into that later, to make sure that the LED intensity and the amount of luminance change is perceivable for the participant, but that's not too easy, right? So this is how this could look like, how it looked like during the pilots in our lab in Mainz. You see this LED array. And by the way, we decided against really darkening the room, because then you need to take care of darkness adaptation, time. This causes additional delays. Also, these LEDs can be very confusing after a while if it's dark in the room, and then everything starts moving, right? It's swaying. So it can be done in a normally lit room. And here's the button box, and you can see the two cables. They actually go to like EEG electrodes on the head to measure the signal. So here in green, the electrode positions for the tACS electrodes, and in red, the positions for the EEG electrodes to measure the tACS artifact from the scalp. This position has been chosen after a bit of piloting, as it sufficiently well measures the artifact for all 3 montages, right? Which have different intensities, different distribution, etc. But this works, even though the signal might look slightly different depending on the stimulation intensity and the impedance of the electrodes, etc. But I found a solution of fitting a sine wave basically to this noisy data to be able to even extract from slightly more lower quality data a proper phase, because the stimulation frequency is known. Yeah, I've shown that already. And then the question was like how to fix the electrodes. We wanted to have these larger rubber electrodes, and I don't show these images, but I had messed around a lot with a lot of gel and electrodes in the beginning, and we easily got shortcuts between electrodes, and there's also the question of like how to position it reliably across labs, then go there with a measuring tape, etc. And so we're basically now using EEG cap, and so this has been developed by Umair Hassan, where we put in the specific EG1020 locations 3D printed electrode holders, in which we then place the 1020 electrode paste and the electrodes, and there are also holders for the EEG electrodes. And by this, you don't need to measure for each subject. You have to choose your correct cap size. You should have 3 of them, maybe 56, 58, 60 centimeter head circumference. And then it can be applied relatively easily. All the hair can be moved to the side. It can be filled with gel. Also, 1020 paste also on the electrode side. Stick it on top. And then we ensure it with another head bandage to make sure it's pressed against the head and it's not moving. Here, the 2 electrodes below the eyes can be fixed just with tape. So this seems to work pretty well, and there will be a step-by-step documentation of how to construct these caps, and the 3D printed parts can be provided, or the cut files can be provided to actually print it. Now, we have these different montages, right? And so we always use a combination of electrodes. For example, for the main montage, electrode OZ, O1, O2 as a one side, basically, of the circuit, and then ZPZ, ZP5, ZP6 as the other. So we have to split from one channel, because we're working with a one-channel stimulator, or we're assuming that most people would be working with that. We have to somehow put this together, right? And the simplest solution is, of course, these Y cables or jumpers, but it's pretty frickly, right? And they easily fall apart, and the connection then might be bad. But this might be the only solution that maybe your ethics committee is going to allow, because you're not largely interfering with the stimulator circuits, at least when you buy them from the respective company. But to make it a bit more practically feasible, Umair then built this montage switching box, which is basically looping the current to the respective channels depending on the montage, which means that you do not need to switch around all the cables in the breaks between the blocks, but you can basically select manually which montage it is, or as a more sophisticated version, even this box would be able to do this automatically, triggered by the Arduino device that controls the experiment. So if you go for the fully automated version, you wouldn't need to do anything, and the Arduino device is also doing the montage switching, ensuring that the correct montage is selected for each block. Because, of course, we have this factor of human error otherwise. But it could be that your ethics committee says, well, this is even if we give them the circuit board, which you're happy to do so, would say, well, it's not a certified part of the system, you are not allowed to use it. In that case, you would need to go back to one of the passive options. So if you would buy the entire stuff including the actual device, this Arduino device, the caps, 1020 gel. If you would use the EMLA cream, by all the electrodes, etc., it would be about €2,000, plus whatever you need to compensate your participants. If you don't use the EMLA cream, and if you would use a system that has already been installed and like borrow it from one of the other groups, it's more like €400. Right? And at the moment we have 7 complete systems, but well, not complete yet, but at least the expensive part, like within the steering committee. And the idea is to, like after finishing data collection on one side, send the system to the next side, right? And the idea is only 20 subjects per site, so it's doable in a reasonable amount of time, and we can do this partially in parallel, partially like sequentially to minimize costs and increase the number of labs that can participate. So the procedure is, it is in rough steps. The first, if you do this, if you have ethics for that, and if you want to use higher intensities, administer a topical anesthetic to the electrode side to reduce cutaneous sensations. And then administer the tACS cap. The participant check electrode impedances, talk about that later. Place the participant in a chair in front of this LED array, provide the button box, and there you go. First have to do the titration for the visual perceptual threshold of LED luminance. Use a staircasing procedure that gives you, is it 2 up, 1 down, or the other way around, it gives you 68% performance accuracy roughly. So not too difficult, not too easy. Then you need to titrate the tACS intensity per electrode montage to make sure that you have the correct intensity set for each one of them. Then you can start the main experiment. And you would need then to select by which mechanism you favor the montage before each of the 9 blocks, and provide a questionnaire after each of the 9 blocks. There will be a detailed documentation, including explanatory videos. All procedures will be made available. We might also have like remote trainings via Zoom to make sure that the procedures are standardized as good as possible across labs. And we hope that the remaining variants that will happen will be compensated by the numbers. If we look at the timeline of preparing the setup and the preparing electrode positions, well, if you do the EMLA cream, so look, anesthetics, applying that, well, it doesn't take too long, but then you have to wait for 60 minutes for it to take effect, right? This prolongs the study time quite a bit. And then you have to actually afterwards wash it out again and blow dry the hair again to be able to then administer the electrodes. But only a few labs will do that, I guess. Impedance measurements, titration, etc., and then main experiment starts. So if you go for the full thing, including EMLA, it's about like 4-hour experiment. Most of it is preparation, so the actual study time is like 1.5 hours. And if you don't use the EMLA, the total time of the experiment is more like 2.5 hours. Right? To me, that doesn't sound too long. I mean, the TMS EG stuff I'm doing is typically taking like 4 hours and longer. So, but it is not just 1 hour. Not going into details here. This is about the specific way the EMLA cream should be applied. So what's the dose and how you distribute it for each electrode site, etc. Can come back to that if there are questions. So regarding impedance measurements. So we decided so far not to use any kind of smart device that would redistribute the current within like these multi-electrode montages according to the impedance of the individual electrodes, right? But there will be variance. The impedance under one electrode might be a bit larger than under the other, and then because it's not separate channels, but it's a split basically of one channel, the current will distribute differently according to the impedance. And of course, we don't want to have completely asymmetric current distributions. Especially maybe not across hemispheres, that is only a unilateral stimulation eventually. Even though it is not super problematic because it will average out across subjects and it would not differ between experimental conditions, right? Not a systematic confound, just a bit more noise. Measurement of all electrode pairwise impedance is not really feasible unless we do it via the automated montage switching device, which we have thought about. Maybe we'll implement that, but I guess that most labs won't use that. And the pure measurement of the montage-wise impedances, so what's the impedance like in the stimulation circuit, doesn't tell us anything about how it's distributed, right? And that voltage, I mean, the voltage will be applied in a way that it compensates for the impedance to reach the desired current, so it doesn't help us a lot. So maybe we go for some kind of scarce sampling of the most relevant pairwise impedances as a compromise. I'll show that afterwards. But even, like, what do we do if there's some asymmetry? If you've ever worked with the 1020 paste in these electrodes, once you got them in, I mean, they have quite a size, right? Once this is stuck in the hair, removing this, going back to the skin start cleaning with alcohol again, I mean, that's not really an option. You will mess it up more than you help it. And so one could either, if it's too bad, say, okay, we dismiss the participant, or you do it nonetheless and just document it, and then we can later see whether this information would explain some variance. But we just trust in big numbers and hope that we'll eventually don't have any problems because it does not systematically confound our experimental variable. Because it is quite a number of combinations, right, that you could measure. This is from one pilot experiment, and like where to draw the line, right? I mean, how much difference would you allow? If you express it in percentage, you easily end up with large percentage differences between 2.1, 4.3 kilo ohm, even though both are super low. So what one could do is just to make sure it's not strongly asymmetric, just measure between like certain pairs to get an idea of whether the current is like more shifted to the left, more shifted to the right. This could be useful information actually to reanalyze the data accordingly. And I mean, the impedance within a set of electrodes, like the central electrodes or the occipital electrodes, that's not super useful, right? Because they will always be connected with each other and never against each other. So we can't really use that, or would actually need to sample all of them and then try to estimate the way the current is maybe distributed within the occipital or within the central electrodes. But I think this is going to make everything way more complicated and cumbersome, and we have to make this protocol sufficiently lean and practical so that labs can actually participate. Then we did a number of threshold titration procedures. First, we had a slowly changing step size. We changed this to a more adaptive change. Didn't make a big difference, but I'm just skipping through this. So we have just tested in a number of subjects whether this algorithm converges, and it does typically, and we can nicely define the visual threshold before we start the experiment. Then the threshold and the hit rate is sufficiently stable over time. Because the question was, do we need to retitrate this in between blocks to ensure that we have the same levels? But this retitration takes so much time that the experiment gets even longer. So therefore, we tested it in a few subjects, and also like with and without retitration between blocks, and it doesn't seem to make a big difference. So we decided against retitration unless, and that's still an option, if the performance drops too far or is too good, basically, that you have ceiling effects or that you get floor effects, because then we couldn't measure any modulation by the phase anymore, and then we would need to retitrate, but only on demand. And typically, it looks like we would not be needing to do that. Yeah, basically that's what I just said. Stays relatively stable, and it seems we don't need to retitrate. Now, the second thing we need to titrate, beside the LED luminance changes, is the stimulation intensity. And this is also just data from a couple of subjects shown here, where we also looked at the cutaneous threshold and the phosphine threshold for the 3 different montages. Also, while doing the task, or without doing the task, because we were wondering whether this would make a big difference on like depending on where you put your attention, whether you're going to perceive these phosphines or cutaneous sensations. Most important thing to take home here is that most subjects, and here another two, so we typically can reach roughly these 2 milliamps, sometimes a bit less, right, for the occipital montage before we see, before you start feeling anything. We typically never reach the retinal, so the retinal phosphine threshold, because due to these large return electrodes here in the central parietal region, you hardly see phosphines. You first start feeling something with increasing currents before you would start seeing something. So we never come to the phosphine threshold, which is fine. So we have to typically stay at 90% of the cutaneous rhythmic sensation threshold. For the retinal montage, very low currents are sufficient, right? I mean, it's optimized to stimulate the retina. So, and the retina is way more sensitive to these currents than your brain is. So it needs not a lot to get to the phosphine threshold. You will not reach the rhythmic cutaneous sensation threshold. So you typically stay below 90% of the phosphine threshold for that montage. And for the cutaneous, also because it's designed in a way to strongly stimulate the skin, while it will never get somewhere near the eyes. We'll never reach the retinal phosphine threshold, but rather at some point the cutaneous threshold, and you will reach that earlier than you would do for the occipital montage. Long story short. Oh yeah, by the way, we also tested this without the EMLA cream, and well, depending on the subject, so with like hardly any to about 50% reduction in the sensations, and which means like reaching higher currents is possible. Typically not like 4 milliamp or something, right? So because I mean, you can apply 4 milliamp with a lidocaine without it being painful, but it feels like someone is like pushing and pulling your skin at 10 hertz, so you can definitely feel it. So you can't go much higher than 2 milliamp. And of course, one could even discuss whether we would want that, right? Of course, we've heard again that high intensities are not necessarily better. But for tACS, of course, things might be slightly different than for tDCS. So, yeah, summarized again, for the occipital montage, the cutaneous rhythmic sensation threshold is typically reached before the phosphine threshold, and so we can stick to 2 milliamp or 90% of that cutaneous threshold. With EMLA, we can go a bit higher in the intensity. For the cutaneous control montage, this sensory threshold is reached before the phosphine threshold, so we can stick to 90% of the cutaneous rhythmic sensation threshold. Typically, in our test subjects, we always stay below 2 milliamp because otherwise you would reach that intensity. With EMLA, you can go a bit higher. With the retinal control montage, the phosphine threshold is reached before the cutaneous rhythmic sensation threshold, so we stick to 90% of phosphine threshold. And this is always way below 2 milliamp. and we will not use EMLA near the eyes, right? This is too dangerous. Then we had started with very sophisticated, very nice questionnaires in the beginning. This is good if you do one study, one experimental session, and then you apply these questionnaires. But we had to do this 9 times, and it just took way too long, and the participant got annoyed and would just cross something to make this go away. So we said, okay, we need to consolidate it to make it feasible. We're just asking after each block for the most important things, and also in a tiered fashion. So, like, do you see flashes or flickering of light? Yes, no. If yes, then we ask, okay, please rate between 1 and 10. Do you feel stimulation of the skin, like burning, prickling, tingling? Always yes, no first. If yes, then we ask another question, right? Do you feel rhythmic sensation on the skin? That's an important one. Is the stimulation painful? Of course, also important in general. Do you feel better taste in mouth? I think we included that because that had been reported more regularly for higher currents. In case we go for the EMLA cream, we wanted to have this checked. And do you feel any dizziness or nausea? So the analysis pipeline has been set up by Benedict. The scripts for that are basically already online on our GitHub. First, of course, we extract all the relevant information from the data, the tACS signal, the target timing, the responses, etc. Do the sine wave fitting that's shown here, which even works for noisy data that we collect with EEG electrodes from the skin. That also works nicely as we've tested. And then a regression model is used to test how well the tACS phase predicts perceptual outcomes, which gives us a regression coefficient per participant and condition, and then group level analysis can be done. And the idea is to analyze the data from all labs at one site, but also, of course, have other labs analyzing the same data to make sure that that's like not one bias or one bug introduced by one person. So what's our status at the moment? So we finished design, task, and protocol. We almost finished piloting. Even the feasibility of montage switching has been tested to a certain degree to produce these kind of instructional videos, make a few last decisions, and then we could basically go for the pre-registered report. So turn our protocol into a manuscript that we're going to submit for stage 1 process, and at the same time the participating labs, which we will check again with all of you who have indicated interest, can then start applying for ethics. At some sites this takes 6 weeks, at others 6 months, right? So it's good to start in time. We're going to share ethic protocols to make sure we apply for the same thing, but of course you have always local requirements, so therefore every site needs to do that by themselves. Then data collection, analysis, and writing the final report. Like here in a few more steps. So basically we're now drafting this registered reports, and the target journal that we had discussed also with the respective editor is Nature Human Behavior. So far, we have about 30 labs that indicated interest to collect 20 subjects. If we actually make that, then we would have about 600 participants, which I think is a pretty good number to even find very small effects, right? At the same time, we can also pool data, stratify it, bootstrap it, see like how many subjects do we need to find these effects. We can look at interlab reliability, etc. Data will only be shared in anonymized or in pseudonymized form. Demographic data will be like detached from the participants, so that groups will basically submit average age and distribution or gender sex distribution, but not individual case information, which makes it way more easy with data safety regulations. Statistics will be based on classical frequent test hypothesis testing, but also base factor. And yeah, I guess it would take a while to have all the data acquired. Well, first to get ethics, right? And then we can have up to 7 labs running this at the same time, and then hand it over to the next lab. In some labs it will go very fast, in others it will take a longer time, so hard to predict. But I mean, we're 4 years on it, so I think no one can stop us now, right? I mean, even if it takes 2 more years. And that's it for now. So that's basically the update where we are. I think we're almost good to go. But yeah, I think we're happy to take questions. Thank you. Are there any questions, suggestions? Yeah. Maybe you can have a microphone, yeah. Because then also the others can hear it remotely.
Thank you very much. Just a short comment about this ethic. I see that each center should submit local ethical proposal, but I think it will be helpful if some group already have ethic votum for this, that we will receive information about this votum. We can submit local to our ethic committee just to show this already similar study accepted. It makes our lives then easier.
Of course.
Ethic,
so I'm happy to take a lead there. So, we're relatively lucky with the ethics committee in Mainz. So once we've written up the proposal, we should have positive approval typically within like 6 weeks or so. And then we're happy to share the proposal, which you would then need to map on the forms and requirements of the respective local committee. Yeah.
It's proposal and also votums that we can submit just to, sometimes our OT committee always wants to know information is similar, study already accepted, and then it's easier then.
Yeah.
Thank you.
Over here, Walter.
Usually we have the problem that we have not enough participants. The ethical committee says, well, we need a effect size estimation, and now here we tentatively have the reverse problem. It is also unethical to have to swallow too much research resources if you can answer the question, let's say, with a fraction of the number of subjects.
That's actually a good point you raised there. We haven't discussed that. It was so far more based on the interest in participating, and so this is how we found out that we would have a realistic chance of like 30 participating labs. Let's see what actually happens eventually, right? I mean, typically it's then a few labs less. But it's a good point. So an ethics committee could basically make the point that you do not need 600 participants, and you should not if there's a relevant effect, right? Yeah, so I'm actually happy to give this question to the other colleagues of the steering committee zooming in, if someone has an idea.
I think it is a valuable point, but also I think what one question was the site-to-site replicability. So I think it was not only about getting the data together and then see what happens. So I think it might be worse in the ethics application to say that it's also about replication across sites. Then the question would of course be how many sites you really need. But I think that the point of another thing which one could think about could be adding an age effect into, if you have so many, depending on how many sites are participating.
You have a comment on that topic? Okay, Gesa?
Yeah, I think this is a very good comment. Couldn't one do a power calculation beforehand, or did you do that for a small effect? Because I think this could not only be raised by the ethics committees, but maybe also during the process of the pre-registration.
Yeah.
So yeah, maybe it would make sense to assume small effects, and I don't know how one accounts for expected variability across sites, because I mean, you can't really account for that. That would be the second question, if there's any chance of getting a training, so of sending someone to one of the steering committee labs to really make sure that we're doing this correctly.
Yeah, I'm sure that would be possible as well. So if the documentation and the videos in the like remote training is not sufficient, then I think this would be an option. But yeah, so I think this is something we definitely have to take as a comment and discuss during the next meetings, how to deal with the effect size issue. Because so we did not do any formal power calculations. I mean, when searching for the paradigm, this was one, like in principle, that some 10 Hz stimulation could have a phasic effect on detection. Was something that has been replicated across a few domains a little bit, right? But there are not so many studies, right? And I wouldn't really feel comfortable, based on these few studies, make these power calculations. I mean, I'm not against power calculations, but it's just assume small, which is a convention, right? Of course, yeah. I mean, honestly, when doing power calculations, you just have to make the correct assumptions to come out, like to get the outcome you want for your proposal, right? There's Simon.
Yeah, so I think it's worth to remind ourselves why we came up with this initiative. And the reason why we came up with this initiative was a huge amount of frustration of labs not being able to see any effects. So therefore, I think if we would have the problem of seeing effects that are so strong that we will have, too many participants, then I think that, that would be the goal accomplished. And we can say that indeed there are effects and we can estimate their effect size, and then any subsequent study can use that, and we will have a faithful calculation of that effect size, because indeed we have many participants. So I would be very happy to have that problem. So I don't think it's a problem at all.
I think that's also a good point. I mean, we could say that we don't just do a confirmatory testing here, right? I mean, we would like to actually estimate the effect size properly, and therefore it's good to have a larger sample than may be necessary. Yeah. Are you raising your hand again, or is it just still? Okay.
No, I think that's actually what I think is important to write in ethics. It is really about being able actually to estimate, but also to estimate the variability across sites. And therefore, I think it's important that the sites also come with enough data. So I think the only power estimation we really need is how much does the contribution from each site to be needs to be to see a local effect. So would that be a medium effect size also on? But I think that is actually the endeavor here. It's about replicability across sites and looking, even if you do the best standardization, how much variability is there still across sites, and that's exploratory in nature.
So that means that maybe the 20, which has been just a guess so far, and something where we would say, okay, that's something that each lab could easily do, would be too low per site, right? So of course one could alternatively say, well, we don't go for 20 and have 30 labs, or go for 30 and have, or go for 40 and have even fewer labs willing to participate, and have a better chance to estimate the local effect size as well. So this is something we could debate. Because, I mean, these numbers are not set in stone, neither the n equals 20 per site nor the 30 labs, right? I mean, this has historically evolved, but it's just an educated guess.
And another thing one could imagine is a Bayesian kind of cut-off criterion to stop the study. So that is that you say, okay, if we have a very strong evidence for the main outcome measure, then maybe you don't want to go for another 200. But I think this is a little bit difficult because we really get heterogeneous data in from different sites, and it would be actually really important to have such a training effort, because that would also be important for future trials, because this is also a network that could then in the future do studies in a coordinated way. So it's really kind of important to get the network activity going.
Yeah, I agree. So, I mean, I think this is not written down yet in the protocol. The limits for, like, I mean, we discussed that we want to use the base factor to decide during data collection whether we want to at some point abort the study, which could go in both directions in principle, right? But the effect is like so strong, we say, okay, now we don't need to like waste more resources and have like more burden and include more subjects, and we can already estimate everything nicely, or the effect is definitely not there, and we don't need to do another 200, yeah. So we need to actually make this more explicit and write down those numbers and expectations and the procedure in the protocol. Yeah. Walter.
We published in around 2008 with Ryuta Kanai as a first author in Khan Biology a paper where we claimed that with an occipital central montage we could induce cortical phosphates with alternating current stimulation. And this interpretation was later challenged by Schutter, arguing that the far-field potential to the retina, which is at least 10 times more sensitive, was sufficient also from this montage to elicit retinal phosphates. So I saw in your overview when you mentioned the threshold for the retinal montage for phosphines, but not for the occipital montage for phosphines. So I think you should also here
so
at the very lower.
So this is we never reached it because we had this like two criteria: cutaneous rhythmic sensations or phosphine thresholds. And whenever we reached one of the two confounders, basically, we stopped and went to 90% of that.
Okay.
So the montage, the occipital montage, our main montage, is designed explicitly not to produce strong currents in the eyeballs. And so this has been modeled also by Axel, also including the eyeballs in the model. Come on, almost there. Yeah. And it's so I have to move this. So while you can see for the retinal montage very strong effects in the eyeballs, they're basically you can see that well right here, but there's basically nothing in the eyeballs for this montage, right? And there's hardly anything in the frontal cortex because of these large electrodes at the midline that would catch all of these currents basically this before they would enter somewhere at the eyeballs. Of course, in principle, one could quantify the phosphine threshold, but you would need to go to really high intensities, and maybe even intensities that would not only you would feel rhythmically, but that would be uncomfortable.
So if I got it right, you stop increasing the intensity as soon as you have a somatosensory perception threshold.
Yeah, so if there's rhythmic sensation of like 10 hertz sensation on your skin, then we can't go higher in the experiment anyway, because we would have a confound that might entrain the brain, right? And therefore we, phrase differently, the phosphine threshold for the occipital montage is so high that we can't reach it, which is a good thing. It means that we have designed the montage in a good way, right? And it's, I mean, that's the main benefit of this study, that has these two very high-level control montages that test explicitly the retinal and the cutaneous confounders. And so we might reach actually much higher levels of retinal stimulation in the retinal control montage than we ever reach in the occipital control montage. And we've discussed, could it be a problem that even at 90% for spleen threshold, you're stimulating the retina sufficiently strong to get some retinothalamo-cortical entrainment effects, right? But if that's the case, they would have, due to the conduction time, a very different phase relationship. So we thought, okay, we're rather on the conservative side and make sure that we are definitely stimulating the retina as strong as or stronger in the control montage than in the experimental montage, right? Yeah. Any further questions? Yeah, there.
Hi. So thank you very much for your very interesting presentation. So I have a question regarding the specific application of tACS, which is also very interesting and very cost efficient. So, but as far as I recall, but maybe I'm wrong, you don't do an a priori assessment of the impedance, right?
A priori.
So you don't, before the application of tACS, you don't measure the impedance.
We do.
You do measure the resistance.
Yeah, that's, there was this entire, well, I mean, well, the, it's still a bit under debate, like how we measure it, right? Like how detailed we do this year, right? Because in principle, we measure all pairwise impedances. That would be unfeasible unless we have a fully automated circuit for that. Or do we just measure a few of them to check imbalance, right?
But you don't use it as a criterion for the application of tACS. So to say, okay, if impedance is above a certain criterion or above a certain threshold, we don't apply tACS out of feasibility considerations.
No, I think we would need to, right? Because if the impedance is too high, then the system would likely shut down as soon as it starts stimulating.
Okay, good. Yeah. So I was just thinking about it from an ethical point of view because of well, noted side effects of tACS in terms of burns. Okay, so well, it's clear to me.
So what is one complicating fact is, of course, that we do not a priori limit the type of device or the brand that is to be used, right? Because this is not testing one single device, and we don't want to exclude any labs that use like different brands. I guess that many will use simple one-channel stimulators, and I mean, most companies having certified stimulators, they also have safety circuits built in, which would stop the stimulation when the voltage exceeds, for example, 20 volt. Or and I think this is something we should maybe write explicit in the protocol to make sure that it's consistent across labs when they're different devices with different default settings, maybe. But yeah, we would not accept participants using like garage-built devices that do not fulfill minimum safety standards.
Okay, thanks.
Thank you. Yeah. Oh, just a second, so that the. Oh, there. Yeah, thank you.
You mentioned that retinal, the current intensity would be at least as high as in the main montage?
In the eyeballs.
In the eyeballs. So at least as high or higher. But if it's higher and that montage also produces effects, wouldn't that complicate the interpretation?
Yes, I mean, so that's the point I made earlier, that, well, the currents it produces in the occipital cortex are always very, very low. So really low, that's not a problem. If the currents produced in the retina would, even at 90% for spleen threshold, produce some retinothalamo-cortical input, right, and rhythmic entrainment of the visual cortex, then this would be a bit of a problem with the interpretation, so we've discussed it actually a lot, but we came to the conclusion that because it would have very different delays, it would strongly differ from the experimental montage where we directly stimulate the cortex, right? So it would be at least like 40, 50 milliseconds longer, so the phase relationship would be completely different. It could not like produce like a false positive in terms of mimicking exactly the results we would see for the main montage.
So, but we could all...
Okay. Thank you, bye.
So what typically happens, as far as I understand, is that often the optimal phase angles varies across participants in different tACS studies. So assuming the phase angle is always the same for the main montage and it varies for the visual montage, then we could dissociate them. But if they both vary, then...
Well, I think it's fine if they both vary as long as they would differ between the two montages within the subject, right? That's what you would expect. So even if, right?
Yeah. And so you have pilot data on this paradigm, right?
Yeah.
And
yeah.
Do you see an effect with the retinal montage?
Well, with technical piloting data. Right?
Ah, okay, so you haven't actually, okay.
So with, I think with a couple of complete data sets that have not yet been analyzed in detail, but I wouldn't make any judgments now based on 1, 2, or 3 data sets, right? Because I don't expect to find anything. So, therefore, I mean, we had this entire discussion also, should we do real pilots first before we go for the main experiment? And went forth and back, and then we decided, well, no, we'll only do technical pilots, because otherwise, I mean, a pilot to judge the effects, whether they're there or not, makes only sense if you have a large sample, and then you already have your study, right? So we can pilot all the technical aspects, but we can't or we don't want to pilot the full paradigm in terms of do we see effects or not, right? Because, yeah. It would not be the right basis to make any judgment to have 10 or 20 even. Yeah.
Okay.
Thank you. Given my experience, I piloted the experiment here at CIMEC last year on tACS challenge. Given my experience, I've seen that in each session, the last trials were always worse than the first, like in the last 30 trials per each session. So I thought it might be maybe useful to shut down the LED for like a couple of seconds every 25 trials, for example, to avoid like, because the sites start blurring after a while, fixing like the light. So it might be helpful to shut down for like 3 seconds every 25 trials to relax the sight, relax the vision.
Like
I don't know, it's just a suggestion.
Close the eyes, you mean?
Yeah, also close the eyes, but if you close the eye, you might miss a light that change in brightness. So the idea I had was maybe to shut down like 2 seconds every 25 trials or something like that. I don't know, maybe you have a better idea.
Okay, so basically when participants would do this for a longer time, would be uncomfortable and they would start also blinking maybe, and of course sometimes they would blink and would not see a target, and we wouldn't know, right? And if you would ask them to close their eyes at specific time points, but keep it open, like without blinking for the rest of the time, that would be
but you have to stop also the task, say, when you ask the participant, because otherwise maybe you, as I said, you might miss some light just because you close the eye. And I mean, I realized on myself, because when I was trying, I see also myself that after a while, after 50, 60 trials, you start like I don't know how to say, the site is boring, and I don't know how to explain. So you might miss and you might decrease because of that and not because of the proper task. So
yeah, I mean, in our piloting in Mainz, the performance remained relatively stable throughout the entire experiment, so it didn't seem to have like huge consequences on task performance, like the time on task. And we have the different conditions balanced in the Latin square form, so that at least we would not have a systematic effect on one of the conditions, right? But it is a good point. Maybe if we do a bit more piloting, we have a bit better idea of like how feasible it actually is and whether we can do something about it. I mean, if we first prolong the task quite a bit, if inducing more breaks with closed eyes, open eyes.
Otherwise, we might shorten like 50 trials and do two sessions per each.
I see the problem. So I also think that the luminance difference between the LEDs in the room shouldn't be too large. So if you go for a relatively dark room and bright LEDs, this is very annoying. If you go for rather low LED, like base luminance level, which is then modulated in a comfortably lit room, these effects might be much less, right? But so we can standardize the LED base level, and we like recommend one. But what we can't really standardize is how the room is lit, right? We just say, okay, normally daytime, like working environment light, not strongly dimmed.
That would help for sure, but also, I mean, shorten in some way could be helpful. Just a suggestion. Maybe you might discuss. You. Okay.
Thank you. Good. Any more comments from our remote participants? Oh, what? Chat again. Don't need it, huh? See what it is. The phase of worst best detection performance would differ between A and B within participants. So, Simon, what was this relating to?
That was just a comment that was discussed 5 minutes ago about the phase difference when we stimulate in the eyeballs or we stimulate occipitally, that although the optimal phase between participants might differ, a participant should show a stable phase difference between the eyeball stimulation and the occipital stimulation.
Yeah.
But I think you answered that.
Yeah, okay. So I just didn't see the comment earlier. Okay, so how are we doing in terms of time, actually?
Should also get some time for posters.
Oh, yeah. Okay, so then thanks a lot. Also thanks to our Zoomies. And then I close the session. Thanks a lot.